Welcome back. This is going to be a lecture on topological spaces, which I thought I could easily knock off in an hour, but I'm not entirely sure that this is going to happen. So we'll see how far we get. So we're going to make topological spaces in Lean, and I'm not going to import anything, right? Well, I'll import tactics because we love tactics, but I'm not going to import any of Lean's topology. So we're going to do the whole thing from first principles. So let's go. So let's make topological spaces. What's a topological space? It's going to be a type class, right? Topological space. What's a topological space? It's going to be a predicate. I guess it's going to be a special collection of sets called open sets. So it's going to be is open. Topological spaces in Lean. Is open is going to be a function that takes in a subset of X. Oh, so maybe I should say, maybe one thing definitely worth stressing. Remember, in Lean, set X means the type of subsets of X, or if you like, the type of sets of elements of X, right? What is a topological space? Well, the first thing we need is a concept of what it means for a set to be open. So we have a function that takes in a subset of X and it returns true or false, depending on whether it's open or not. So that's one thing. That's the main thing a topological space has. That's the structure. And then we need a bunch of axioms. And so what are the axioms for a topological space? I guess the whole space is open univ. That says is open. That says X itself is open, but X, you see X isn't a subset of X. The subset of X called X is called univ. So I need to, well, it's called set.univ. If I put univ, yeah, I get an error. Let's open set. There. So there we are. So what's going on here? This says some subsets of X are called open sets. There. This one here says X itself is open. And now what is open inter? That says the intersection of two sets is open. So intersection of two open sets is open. And how would I say that? I would say that would be that for all u and v, for all u and v subsets of X, if u is open and if v is open, then u intersect v is open u intersect v. There. That's kind of annoying that we can't see it, isn't it? How about we put it there instead? Maybe the comments go here. Right. So the class definition of topological space. Wonderful. Some subsets of V are called open sets. X itself is open. Here's where the comments go. Look, they fit much better there. The intersection of two open sets is open, and then I need an arbitrary union, right? Arbitrary union of open sets is open. There. And so what's that going to be? Is open. Let's make it a set theoretic union. I think this is what they do in the maths library. So what does this say? This says for all I need some curly letter. Let's go for curly C. For all curly C, this is a collection of open sets. Sorry, this is a collection of subsets. So I've got a set of subsets of X, and let's make sure that they're all open. For all u in C, is open U. So that says I've got a collection of sets and they're all open, and the conclusion is that the union is open. So what's that? Big cup 0 C there. No, there. And then close the bracket, and that compiles. There we go. So that might be if I've got it right. Have I got it right? Looks right. Open sets. The whole thing is open. Intersection of two open sets is open. Arbitrary union of open sets is open. I think that's okay. So this is kind of, I never quite know, when you're doing arbitrary unions, I never quite know whether you should do, so what is an arbitrary union of open sets, right? So the way I've set it up as a set of open sets, right? But you might have an indexed family, right? An indexed family of open sets, i.e., some set. How would that work? i.e., some type kind of iota there, and then for all I in iota, an open set UI, right? And then you want the sort of the union of the UI is open. So this is some slightly, I mean, you have to just say exactly what you mean by an arbitrary union of open sets is open. So maybe the first thing I should do is sort this out. So let's go into the topological space namespace. Namespace topological space. And now let's end this as well, so we don't get any errors. There we go, no errors. So let X be a topological space, right? Let X be a topological space. Topological space. So that would be variables. Variables. X would be a type, and it would be a topological space. It would be in the topological space class. So there we go. So now let's do index unions. So how about this then? So lemma is open union. So you see, I put S union here to indicate that that's some sort of set theoretic union. And then without the S, this is some random union. So now here I would have iota, a type, and I would have a function from iota to set X. So now you see I've got a random set iota, and then I've got a function that, given an element of that set, gives me a subset of X. And let's have the hypothesis HF that says for all I in iota is open f of I there, and the conclusion is supposed to be is open, the union of these things is open. So that would now be that would just be big cup iota fi, right? Is that the thing? No, is it big cup I? It's I always get the syntax wrong for unions. The union over I of fi. Yeah, that sounds right. Great. So all I'm doing, this is some sort of technical thing we may as well get out of the way now. What does it mean for an arbitrary union of open sets to be open? Do I just mean a set of open sets, or do I mean an index family of open sets? So this should immediately follow from the set theoretic version. So let's just apply this. What happens if we apply this? Great. That's worked great. What about the empty set? I want the empty set. The empty set, Kenny, I think the empty set is going to be the union of, I'm going to get empty. Yeah, I'm going to prove the empty set's open because it's an empty union of open sets, right? Yeah. That's where we're going to go. We'll do that next. Okay, promise I'll do empty set is open next. Yeah, because when I was taught topology, I was told the empty set being open was an axiom. This should be easy though. let me just finish this. This is just some stupid technicality. So intros U and HU. What's the question? I know that U is in the range of some function. So that means this hypothesis says that U equals f of I for some I. So I can probably do cases on it, can I? Cases HU with IHI or something. Does that work? It does. And now HI has got a let's just cheer up HI. Great. Wonderful. So now I know that f of I equals U, so I can rewrite HI or the other way. And now I've got to prove that f of I is open, and we know that f of I is open for all I. So apply HF, and the goals are accomplished. So there we go. That's some technical thing. That could have been, yeah. I could tidy that up. Are people interested in seeing a term mode proof of that? Anyway, we've got a dangling issue with the empty set. Is open empty? Let's prove the empty set is open. Empty set is open. Is open empty? So this says is open the empty set. Oops. Let's try that again. So why is that? What do I want to do? I want to apply is open S union, but with C, I want C to be the empty collection of subsets of X. So let's let C. That's going to be a set of subsets of X, and let's let it be the empty set. Will that work? There. And now let's let C be the empty set, and I claim that every element of this set is open. Have HC. It says for all U in C is open U. There we go. So why is every element of the empty set open? That's a good question. That proof is going to go there. So intro U. Let's let U be a set, and let's assume intro HU. Let's assume that U is in C, and C is by definition the empty set, so that can't happen, right? Case is HU. Yeah, that's the end of that proof. So there probably would have been a fancy way to do that, right? I could probably have done rintro U and no cases at all. Does that work? Yeah. There we go. So there's my fancy proof that there are no elements of the empty. So every element of the empty set is open because the empty set doesn't have any elements. And now what? And so now we should be done by this thing here. So it should be is open's union. Let's do convert. Is open S union. Let's give it C, and let's give it HC, and let's see what we get. And we have to prove that the empty set is what you get when you take a union over the empty set. And is that true by definition? It's not true by definition, but I bet the simplifier can do it. There we go. The simplifier has done it. I have goals accomplished. In fact, how was that done? Let's see what the simplifier did. There we go. S union empty. That's what it was called. So I could do rewrite S union empty. There. Goals accomplished. Marvelous. So now the empty set is open. The whole space is open. And what's the other kinds of? What else am I going to need? Right. Okay. So here's an interesting question. We know that the intersection of two sets is open. Can we deduce that an arbitrary finite intersection of open sets is open? There. Let's do finite intersection of open sets is open. Finite intersection of open sets is open. That's somehow a key thing. And why will that be true? That will be proved by kind of induction. By induction on the size of the finite set, right? So to make sure that this induction proof works, let's just go through this carefully. Let's just check that the beginning is okay. Can I prove that the intersection of no open sets is open? Yes, I can, because the intersection of no open sets is the whole thing. So the base case for the induction will be this. Can I prove that the intersection of one open set is open? That's obvious. Can I prove that the intersection of two open sets is open? That's an axiom, is open inter. And then for three or more, I should just be able to, okay, great. So this should be doable now. So lemma is open sinter. Why don't I do it with finite sets? So let's take a collection of subsets of X. So C is a collection of subsets of X, and then let's have HC, which says it's finite. I'm always slightly nervous about finite things. So we've got a finite collection of subsets, and then let's say, and now what are we going to prove? If they're all open, for all u in C is open U. If they're all open, then is open, and now I've got a brave. Let's see if I've got this right. Is this going to compile big cap 0? You put zeros there when it's a set, I think. Oh, I've put a 9 there. There. Has that compiled? Yes, it has. Great. So now this says that a finite intersection of open sets is open. And this should follow from the fact that the intersection of no open sets is open and the intersection of two open sets is open. So how does one prove this? One wants to prove this. I guess there will be an induction principle for finite sets. So let's apply, it'll be called finite induction on or something. Finite in, there it is, finite induction on HC. There. And so now we should have two cases. We do now, we've got two goals. This is the base case. There. There. And then we should have the inductive step. There's the base case. Let's apologize. And then if we've got the inductive step here. There. Sorry. So that proof, okay, so far we have compiling. We have one warning because we've cheated. So what's the base case? The base case says, the base case looks to me, I kind of feel like that just says is open empty. Well, okay, so let's just do intros. And now we've got to prove, oh, no. This is the empty intersection, sorry, the intersection of no things is everything, right? So this is apply is open univ or something. Is that going to work? It didn't work because it doesn't know. Let's convert it then. Convert is open univ. Let's see what happens if we do that. Great. So now it says you've got to prove that the empty intersection is the whole set. And my guess is that, is that true by definition? It's not true by definition, but my guess is that the simplifier will know it. And the simplifier did know it. And again, I'm interested to know how the simplifier knew that. So it's called sinter empty. So there we go. So it could probably be rewrite sinter empty. The empty intersection of a bunch of sets is the whole thing. Great. So that was the easy case. So now we've got to do the inductive step, and the inductive step, that's going to follow. We're going to use what? We're going to use this thing here. Is open intersection of two open sets is open. So this is kind of a mess. So what do we actually got to do here? So let's let U be a set. And now let's assume something. Let's assume some hypothesis. What does the hypothesis say? Oh no. Let's let C be a bunch of sets, and let's assume that U isn't in C. Let's assume that U isn't in C. Oh, and let's assume that C is finite. There, and now let's assume that everything in C is open. What's that going to be called? There. And Now let's assume something else. Let's assume that what does this say? Let's intro it first. Let's assume that everything in that says everything in C union U, right? So H says assume both U and every element of C. Math cal C is open, I think. For all U, if I'm in insert UC, just means the set you get when you insert U into the set C. So this is, yeah, insert, maybe I should just insert UC. Insert UC means U union C, just to be clear. So an element of U union C is either U or it's C. So that's what H says. And now you've got to prove that this intersection, we've got to prove that this intersection of, right, we've got to prove that the U intersect, aha, so I see. The next thing we need to do is we need to figure out how to take this insert thing, right? This insert command inserts an element into a set. So C is a set of open sets, U is an open set, and insert UC is a slightly bigger set of open sets, which contains all the sets in C and then this one element here. And now when you take the intersection over all those things, it's U intersect the intersection of all the C's. So there's going to be something that's going to be called rewrite Sinter insert or something. Is that a thing? It is a thing. See, good old naming conventions. So now I've got to prove that U intersect this intersection here is open. So I've got to prove that the intersection of two open sets is open. And I'm going to apply this, right? Now is the time to apply this. Apply is open inter, and now I should have two goals. I do. I've got two goals. And my first goal is to prove that U is open, and my second goal is to prove that these things are, and those should both be assumptions somehow. So I've got two goals, so I should do this. There. And my first goal, hopefully this is an assumption. I've got to prove that U is open. I see, and this follows from hypothesis H, right? Hypothesis H says that everything in U union C is open, so I can probably apply H. Can I? I can apply H, and so now I've got to prove that U is in U union C. And I suspect that the simplifier will know that. Will the simplifier know that? Yes. The simplifier knows that U is in U union C. And now what's left, I have to prove an arbitrary. Now again, this should be aha. So HC2, right. So the conclusion of one of our hypotheses is that this intersection is open. So let's apply that. Let's apply HC2. And now Lean says we have to prove that for all U in C, so intros U and HU, we now have to prove that these things are open. And then why are they open? Again, that's going to follow from H, right? We've now got to prove that every element of C is open, and H says that every element of U union C is open. So apply H. And now I've got to prove that if U is in C, then U is in insert UC. I'm not sure the simplifier isn't very good at that sort of thing. Oh no, it has, it's worked fine. Thank you, simplifier. So that is the proof that a finite intersection of open sets is open. Naming convention for the win, exactly. So now what do I want to do? So I guess, I don't know. Do I want to do closed sets? I'm not really sure. Def is closed. What does it mean for C set X to be closed? And it means, I guess it means is open. C. How does that work? Is it this? There we go. So now we've got open and closed sets. And now I could prove things like, yeah, so clearly could spend all day proving facts about closed sets now. There. So I guess, for example, I mean, let's just do one. So lemma I don't know, is closed empty. Is closed empty. That says is closed the empty set. There. And now I wonder if that should exactly be the same statement that should exactly say is open univ, right? So it should be that. Does that no covert? Let's try convert. So now, oh, that's not gone well. Oh, I see. It doesn't know is open univ. Hard luck. Convert is open univ. What does it say? Is open univ says is open univ set x. That's what I think it. Let's try this. I think that you should be very close to saying that. Yeah, it doesn't know that. Is closed. Oh, maybe I should unfold is closed or something. Let's try that. Oh, there we go. Great. So now I've got to prove that the complement of the empty set is the whole thing. And that sounds like the kind of thing the simplifier might know. And the simplifier did know it. Great. So there we go. I could prove 1,000 things about closed sets. But we're already halfway through. So I'm supposed to be going for what? Continuous image of a compact set is compact. I don't even have continuous functions. So I'm never going to make this. So let's do continuous functions. So next continuous functions. I might have to finish this on Thursday, but let's see how far we get. So now what do we need? Variables, sub-unfolding definitions. I needed to unfold. Look, it didn't work, Kenny. Look, it doesn't work without the unfold. It's because the convert doesn't do it. Look, convert refuses to unfold it. So let's have let X be a topological space again. I'm out of the namespace, you see, because continuous functions don't really deserve. Oh, maybe I need two of these things. Y type topological space Y. Okay, great. So what's a function? What's a continuous function? A function X to Y is continuous if the preimage of an open set is open. There. So let's say def continuous. I've got a function from X to Y, and this is a proposition, and it means for all U is open U. You see, I don't. Maybe I should just say this. Let me just finish this first. Is open, and then the preimage. And that hasn't worked because I have an open topological space. So let's open topological space. Great. Now that's worked. So there's my definition. A function is continuous if the preimage of every open set is open, if you like. A function from X to Y between topological spaces is continuous if the preimage of every open set is open. And it's just sort of worth remarking here that I didn't say what the type of U was. I didn't say for all. Look, if you hover over it, it says U is a subset of Y, and I could have put that there, but I didn't put it because Lean can guess, because when I look at its preimage here, right, F goes from X to Y, and this weird inverse with a primed on it, because inverse is like inverse in groups or something. Make a simp lemma, says Kenny. Is closed if. Oh, okay. Right, Kenny wants me to fix this. So simp lemma is closed if. So that's C set X. Is closed C. If and only if is open C complement. And the proof of that is it's true by definition. So the if dot ruffle there. And now what? So now you're telling me I can make this easier. Simp is closed univ. How about that? Does that do it? Oh. No, sorry, is open univ. Does that finish it? It does. So there we go. Thank you, Kenny, because there you go. If I tell Lean how to deal with closed sets, I don't need to unfold it. Right. So there's my definition of continuous, and probably it's worth remarking that this inverse, the pre-image of a set is this weird notation, inverse with a primed, because inverse means take the inverse of the function f or something. Mathematicians use f inverse. Mathematicians use inverse to mean two different things, and in Lean you can't get away with that. So this says the pre-image of U is open, and when Lean sees that, Lean realizes that U must be a subset of Y, and so it's happy with the definition. So there's continuous, and so I guess the moment you prove continuous, let's prove, I don't know, let's prove continuous id. Continuous id. You should prove continuous id and continuous comp, right? The moment you define things about functions, id from x to x. I want to prove that the identity functions. You define a predicate on functions, and you somehow. It's very natural to prove it for id and comp now. Like composite of continuous functions is continuous. So how am I going to prove that the identity function is continuous? So let's do intros. Intro U, let's see what happens. Yes. So let U be a set, intro HU, and let's assume that U is open. And now I've got to prove that when you pull back U by the identity map, it's also open. So, and I pull back U by the identity map, it's going to be equal to U. So here's an interesting question. Clearly, if I pull back U by the identity map, it's U, right? But is this true by definition? There's just an interesting question, right? And so you see, look, and here's another question, another interesting question. Clearly, if I push forward, right? Clearly, if I take the identity map and I do this of U is U, this is push forward, right? But is this true by definition? There. You see, because to a mathematician, we don't care what's true by definition, what isn't true, right? These are not, these questions are not mathematics, right? Are not mathematical questions. Okay, because they depend, they depend not on the specification, but on the implementation. All we need as mathematicians is the fact that the push forward of U under the identity map is U. We need this to be a theorem, and we need this to be a theorem, you see. So I'll just do an experiment. I've just got interested in this now. So have H1, U equals id double primed U, right? There. So let's try and prove this. So we don't need this for this proof, but I've just somehow got interested now. So is U equal to the push forward of the identity function? So let's try REFL. You see that fails. So it's not true by definition. Fails. So let's comment that out. There. So not true by definition. So let's sorry it. I mean, I can certainly prove it, but now let's try the other way. So have H2. U is the identity function, the preimage of there. And again, let's try REFL. And this time REFL works, right? This is back, this is back to the proof, right? So this time you see I've got one goal, I've got one goal, I've got one goal. And then by the time I'm here, I've got two goals. And then by the time I do this REFL, I've got one goal again. So this one here, this is true by definition. And this one here, and this one here is not. So you see that, definitional equality is quite weird. I mean, I can prove this. Let's try and prove it. How am I going to prove it? So let's try extensionality. XX. I'm going to prove that an element of X is in U if and only if it's in the push forward of U by the identity. So this is really not REFL, right? Okay, so let's split it. And now let's intro intro H. I've given up with proving that continuous image of compact is compact. That's going to be next time, because I'll easily do it in 2 hours. And so now I've got to prove that X is in. You see, what's the definition of push? This is kind of interesting, right? What's the definition of this thing here? Unfold set.image, and then we'll presumably see. Yeah. So we've got to prove that U is in the. We've got to prove that X is in the set of X's such that there exists an X such that X is in U, and the identity function. So this is the problem somehow. There's an exist statement. So we need to use X. There. That's why use X. There. This is why it's not true by definition. There. Because id double prime of U is exactly. I see this now. Id double prime of U is the X in X such that there exists an A in U such that X equals the identity function applied to A. And so now you can, yeah, okay. So why is this true? C, I mean, I don't know. Will a tactic do this? Split assumption. I've got to finish this now. Id of X is X. That's true by definition. Great. And now this way, intro, I could do rintro. You see, there's the existence is hidden in here. There's some exist statement, so I could do rintro. What could I do? Rintro kind of y, hy or something. hy1 and hy2. There. So the statement that X is in the push forward of U by the identity map turns out to break down into 3 things. Id of y is X. I could probably replace that by ruffle, I guess. Let's make X equal to f of y by definition. So there we go. And now this is exact. Id of y will be equal to y by definition. So this is exact hy1 or something. There. So there we go. And now let's get back to the proof. What was I trying to do? So the whole point of that was I'm trying to prove that id inverse of U. I'm trying to prove that id inverse of U is. What I'm saying is I don't need H2. I know that U is open. I'm trying to prove that id inverse of U is open, but id inverse of U is U by definition. So this is going to be exact HU, right? Exact HU. You see, I can comment all of this nonsense out, right? There. So you see, I've got that U is open. I need to prove that id inverse of U is open, and I can just say, well, that's exactly HU, but that's because this was true by definition. And if we'd been pushing forward, it wouldn't have worked. So there's continuous id, and now let's prove continuous comp, because these are fun. This is good quality entertainment. So what have we got here? I guess we've got f goes from x to y, and g goes from y to z. I haven't got a topological space z, so variables z can be a type. So let z be another topological space. Topological space z. Continuous comp says that if I've got a function that's f from x to y and g from y to z, and let's assume that f is continuous there, and let's assume that g is continuous there, then the conclusion is continuous g composed with f, right? There. And this should also be very easy. So why is that true? Well, let's intro U. So let U be a subset of Z. So intro HU, and let's assume that U is an open subset of Z. And now, So G composed with F inverse. This is kind of interesting, right? This says change is open. It's G composed with F. F is the inverse of this, of U, right? That's what we're not trying to prove that. What have I done wrong? I just need brackets. There. And so now one might ask, is this the same as if I pull back by F and then I pull back by G? Will this work? Oh, it does work. Look at this. So G composed with F pulled back is by definition if I pull back by G and then pull back by F, obviously it's the same as pulling back by G composed with F, but the miracle is that this is true by definition. And so now I've got to prove that the great. Now I've got to prove the F inverse of. I've now got to prove that the pullback of something is open. That F is continuous. So now I can apply HF. There, I'm doing the proof backwards. So now it suffices to prove that G inverse of U is continuous. So now if I apply HG, so I'm doing the proof backwards, right? Proving it backwards. There. This is the way the computer scientists like to do it. And now I should be left with an assumption. You see, eventually, I'm saying it suffices to prove one of our assumptions. So exact HU. There we go. So that's that was all intros and applies. Look at this. I'll show you. We could term mode this. Continuous.comp primed. Let's do that. There you go. So here's a term mode proof. So instead of intros, it's lambda, right? It's lambda U and HU, and then I've got to prove something. So that's the intro U and intro HU, and then I don't need to worry about the change. I'm in term mode, and so everything works up to definitional equality. And so now this should be HF of something, right? This is going to be HF of something something. Oh, curses. HF says continuous F. What's the definition of continuous? I need to tell it more stuff. HF of, why don't I put this thing here? Is this going to work? Yes, we're back on track. I've got the error in the right, I've got an error, but it's in the right place. So this is by continuity of F, it suffices to prove that G inverse preimage of U is open. So now I've got to prove this, and that's going to be $HG blank blank. Great. So now I've got to prove is open, and so now I put HU here. There we go. So there's the same proof, right? This is the same proof. When you have tactic mode proofs and they only do things like intro and apply, you can just do them in term mode. There's no harm in doing that. So term mode for the win. And this is what you see in MATLib. These are the proofs you see. So now we have continuous functions. Now what then? I guess let's do compact spaces. Subset C of X is compact of the topological space. X is compact if what? If every open cover has a finite subcover. There. So definition compact. What does this say? C. So X will be, let's say, for all for all collections of for all sets of I've got a collection of subsets of X, and let's make the hypothesis that for all U in C, let's make them open, is open U. So that says if I've got a bunch of open sets, and if my closed set is a subset of the cover, big cup 0 of C, then there's a finite subcover. So there exists some F set X such that, so F is a subset of C and is, let's say, is finite F and what? And C lives in big cup 0 of C. So there's my definition of compact. And I think it's maybe interesting to compare, what does the dollar do? Oh, the dollar is the same as brackets. there. That's the same thing. The dollar is look, print. If you know about Pratt parsers, print notation dollar there. That's what dollar does. It has binding power 1. It has extremely low binding power, and so it does the same job as brackets, but you don't need brackets. So yeah, this says that $G means the same as FG, but binding power. This is some trick that they use in Haskell, and was somehow stolen by Lean. Yeah, you can read about the dollar in Learn Your Haskell. That's where I learned about it. So there's a definition of compact, and I think it's interesting to compare with the mathlib definition of compact. So let's search for def compact in mathlib. Let's just look at, oh crumbs, can I search for a space? Oh, bingo. So this is I see that I see. These are mine, and this is Lean's definition. So here's Lean's definition of a compact set, and it's completely different. It says for all f, what's an f? If I hover over f, you see this is a filter. So what does it mean for a subset of alpha to be compact? You see, alpha is a topological space. You can tell this was written by computer scientists because they called it alpha, not x. I've got a subset of alpha, and if every filter, which isn't the bottom filter, every proper filter which contains, what's P? The principal filter containing S has a cluster point. So there you go. This is a completely different way of saying compactness involving filters, but I don't really want to get into filters because I'm trying to, mathematicians are my audience, and I'm trying to explain mathematicians. So there's a mathematical definition of compact, and one could then prove that this is the same as the filter definition. And why don't we do Hausdorff while I'm here? Dev Hausdorff. Set things up for next week, as it were. So what does Hausdorff mean? I guess that's a property of topological spaces, right? Type topological space X, and that's a proposition, and that means this is a proposition as well, right? Maybe I'll put that prop there. These are definitions, not theorems, you see. Oh no, those can go there. Oops, that can go there, right? And what's the definition of Hausdorff? I guess it would be for all x and y in X. If X is not equal to Y, then there exists a U and V in set X such that U is open and V is open, and X is in U, oh golly, it is very long, and Y is in V, and U intersect V is empty. There. So there's my definitions of compact and Hausdorff. And what's the time? I've got 10 minutes left. Well, maybe I'll start. So theorem. So we'll finish this next time. Theorem, continuous image of compact is compact. Continuous image of compact, I don't know what to call it. This is probably called compact map or something. That's probably what Lean would call it. So continuous image of a compact set is compact. Theorem compact map. So this would, I'd have some f from x to y, and I'd have a hypothesis that f is continuous, and I would have C, which is a subset of X, and I would have the hypothesis HC would say it was compact there, and the conclusion is the image is compact there. Begin. It's such a lousy, I don't know. I'll tell you. Let's. I don't know. It's a very bad idea to just leap into the middle of it. And let's do the other one. Let's state the other one. So theorem: compact subset of Hausdorff space is closed. Closed is closed of compact. Let's do with that. So that would say, what would that say? So X is a topological space, we know that. So let's have HX Hausdorff X. And what else would we need? We would need C in set X. And we would need HC. That can be implicit. We would need C a subset of X, and HC would be the hypothesis that it is compact C, and the conclusion would be is closed C. There. Begin, sorry, end. There we go. I mean, I guess I will. It just seems ridiculous. I think both of these are going to be long. I can imagine that both of these would take half an hour. But let me just. I'll tell you what. I'll just play around. Let's just start and let's just see what we have to do. So what does it mean? So Kenny won't let me unfold this. So we'll have to unfold it in our minds. What does compact image of C mean? We can see what it means. You see here. This, I'm going to do it. Sorry, Kenny. If you unfold it, you can see it means something here, right? So we don't. So we should do intros, intro C. There. You see, we don't need to do that unfolding, right? It's not there. And now intro H C. What does that say? So we're assuming that C is a bunch of subsets of Y. That's the target space, and we're assuming that they're all open. And we're assuming that the image of C is in the union of these things. So intro HCC there. And now we've got to come up with, and now this is where we get stuck, right? So now we've got to come up with a finite set. Now we've got to come up with a subset of C which is finite, and this finite. You see, that's what it means to prove that something is compact. So now we're kind of stuck because we're nowhere near ready to. No, I don't think that unfolding is inherently bad. I just think that Kenny's whinging about it because he likes term mode best or something. Here's an interesting question: how many unfolds are there in MathLib? So there you go. 1, 2. Look, there's 684. Yeah, unfolding can't be inherently bad because it's all over the place. Look at that. It's even in data.int.basic. There you go. No, clearly this is a proof that unfolding is not bad, right? Look, the p-adic integers, that was written by an expert. No, unfolding is fine. It's just uncool, right? It depends, how lovely do you want your proofs to look? So now we are stuck because now we're going to have to actually think about how we're going to prove this. And I guess what we want to do is we want to pull back. I see. We want to pull back. We need to use the fact that C is compact. So C is compact. You see, look, this is the idea now. Unfold unfold compact at HC. There. You see, this is the thing we need to know next. HC says we've got a collection of open subsets now of X. And if C is in there, then there's a finite subcover. So every open cover of C has a finite subcover. That's what that says. And we have an IC. We have an open cover of Y. We have an open cover of Y, and to make HC is a function, right? HC is expecting an input, and the first input it's expecting is a bunch of open subsets of X. And what we have is a bunch of open subsets of Y. And so I guess the next line is to let I mean, we could set D to be what? To be the V. Is there a clever way of doing this? We want D to be the. We want D to be the pullback of. Ooh. We might be able to do it like this. If we take the pre-image of. Can we do this? Curses. Great. I'll spend it. No. It's inverse. Curses. That's really annoying. There's going to be some clever way of pulling back all the open sets at once, right? Let me have test. Let's see if I can define D. So what's the type of test? Oh, that's an error. Let's get rid of that. Oh, that doesn't work. Where does that goes from set Y to set X, right? I need to push it forward maybe. I think that should work. I'm quite surprised that doesn't work. Does F goes from X to Y? Okay, let's try. I think maybe we need this. Is this the definition? Let's see if I can get this right. Why doesn't this work? Okay, great. So I'm stuck. I can't get my cool. So where are we stuck? I'll start next time by unsticking myself. We want D to be the collection of subsets. To be a collection of subsets of X given by pulling back all the elements of Y. And there'll be a clever way of defining it that I've somehow failed to do there. And then how will let's just say how the proof goes. D will be, you see the image of C is covered by all the C's, and so C itself will be covered by all the D's, and because C is compact, there'll be a finite subcover, and then we push forward that finite subcover, and that will be end. Right. And I'm going to stop here, and I'm going to prove these two things on Thursday afternoon. So thanks for watching, everyone.